I'm 2 minutes past our time. So let me turn everything over to Brian Goetz, who's the architect for a Java language from Oracle.
Thanks. So, thank you, Frank. So, as you probably all know, because you've seen all the marketing hype, Java is 20 years old this year. That's a pretty big deal, right? And of course, we at Oracle want to make sure that Java remains vibrant for the next 20 years as well. So in this talk, I'm going to talk a little bit about how we plan to accomplish that. Even though, we can't predict the future, we can at least learn a little bit from the past. So we'll start with an easy softball question. How many people here wants to write software that no one uses? So, counter question, who wants to write software that's going to be used by millions or even billions of people? Right, okay, this is what motivates us. Most of us write software for the love of it and the challenge of it, but we also want to write software that's going to be used and remains useful over a long period of time. And this is a natural human drive. We want to do things that are relevant. So for me personally, for the last 5 years, I've had the privilege of piloting the evolution of the Java language. And I love programming in Java, so in part I'm doing this selfishly just for me. But really what motivates me to do what I do is the leverage inherent in improving the language that's used by millions of people. So if there's 9 million Java developers out there, what I do has the chance to affect all of their experiences of programming, their productivity, and their impact on the world. And so I'm going to talk a little bit about my perspectives on language evolution, some of the lessons that I've learned personally from this part of my journey so far, and some ideas about where Java might be going next. So most programmers like to describe themselves as being pragmatists, and this is generally considered a good trait in engineers, right? How many of us consider ourselves to be pragmatists? Not a trick question. Well, a little bit of a trick question. Okay, so let's dig into what that means, right? So Webster says pragmatism is a reasonable and logical way of doing things or thinking about problems based on dealing with specific situations rather than ideas or theories, or a practical approach to problems and affairs. So that sounds pretty good, right? Pragmatists? Yep, all right. Let's dig a little bit deeper. If we asked a philosopher what is pragmatism, we would probably get an answer somewhat like this, which was the pragmatic maxim that was coined by the American philosopher Charles Saunders Peirce in 1878. It's a little bit wordy, so I won't go through it. But again, it's all about thinking about the practical effects on the world around us, rather than thinking about things from a lofty perspective of ideals and values, actually thinking about what effect do we have on the world. And you could sort of sum this up in the words of a much older philosopher. There's no good, there's only good form. Now, Master Yoda didn't really say this, but if he had said this, what he would have meant is that when making judgments about the world, we should look past our own principled aesthetic and ideal beliefs and judge things on the basis of whether they work or don't work. And we should judge the good of something based on its, not on its intrinsic properties, but on what it is good for. So let's try to apply this a little bit to programming language design. One of the things that we learned from studying the history of programming languages is there's no perfect language. And this should be kind of obvious, right? Even imagine in 1962 we did invent the perfect language. For how long would it have remained the perfect language? The world changes. The problems we solve with programs changes. What we know about computers changes. The hardware changes. And if the problems are changing, then the tool that might have been perfect for yesterday's environment is unlikely to be perfect for today's environment. So I think evolution has, is sort of a good way to think about how programs and systems evolve. And to illustrate, how I think about evolution in terms of programming languages, imagine we have an ecosystem where the programming languages are the predators, the programming problems are the food supply, and the state of computing hardware and infrastructure is our environmental conditions. So now we have an ecosystem, right? So now all we have to do is wind it up and let evolution do its thing, right? Over time, the denizens of this environment are going to change, the food supply is going to change, the environment's going to change, and rather than talking about languages as being good languages or bad languages, it's probably more useful to think about languages in terms of whether they are evolutionarily fit for the problems on which they're called upon to solve. And because the world changes, some creatures that are evolutionarily fit for one set of conditions, as their environment changes, they manage to adapt, and others don't manage to adapt and they die out. So I think we all have a little bit to learn from this. And as an example, let's pick a language that sort of has mostly died out, which is COBOL. All right, so who here thinks COBOL is a lousy programming language? See, that was a trick question, right? There's no good programming languages or bad programming languages. There are programming languages that are good for, or not, not good for, the kind of problems that they're called upon to solve. So COBOL was a pretty fit predator in 1960. It was very well solved, very well suited for solving the kinds of programming problems and the computing environment that we found ourselves in the 1960s. The database technology of the time stored records on 80-column punch cards or maybe mag tapes that emulated punch cards. And the most common programming problems were producing summary reports, sales by salesman and geographic region. So a language that was built upon imposing some weak types on 80-column strings and reading into a bunch of records and accumulating some subtotals and spitting them out was actually darn useful in the 1960s. So we may find COBOL to be ugly or unsophisticated, but it really was quite a fit predator for the business problems that it found in the times, just as Fortran was a fit predator for the programming problems of the 50s, which were largely oriented around things like producing artillery firing tables and things like that. So COBOL died not because its food supply ran out. We still run roll-up reports of sales by salesman and geographic region today, but a more fit predator emerged, which was SQL. And so we no longer needed a language that was built around that particular kind of problem. So let's talk about Java. Java may not be the prettiest language, but it's still the dominant predator in today's programming ecosystem. Now, evolutionarily fit doesn't necessarily mean beautiful, but Java is still a fit predator, get it, predator, for the enterprise programming environment. And if I showed you some Java 1.0 code, you'd recognize it. It would look a little different, it might look a little out of date, because Java has evolved over the last 20 years, but, just like in a real biological ecosystem, things mutate, things evolve, and, in our programming language ecosystem, the mutations aren't random, they're actually decisions people make, but just like the mutations that occur in the wild, sometimes they're beneficial and some turn out to be disasters, right? So hopefully, we'll exercise good judgment and they'll turn out to be beneficial, but you never know where things are going to go. If we want to remain relevant, we have to change as the ecosystem around us changes. We have to adapt. But there's a very valid question to be asked of how fast. If you change too quickly, you risk turning into something completely different. So we want to evolve the language, but we want it to stay the same species, as it were. And there are forces that are pulling us in both directions, right? So there are forces pushing us towards more change, adapting to the change around us, changing hardware, changing developer demographics, even changing developer fashion. And, there are forces that push us towards resisting change as well. We have a very low tolerance for breaking our customers' programs. Our users expect Java programs to just keep working. And of course, we don't want to take so much risk. We don't want to risk breaking things, making them worse in the hopes of making them better. And so we're kind of pulled in these two directions. Some of these pull us towards change, some of us pull us in the other direction. And of course, just like in politics, you end up hated from both sides, right? So some people say you're not moving fast enough, some people you're saying moving too fast, and if only 30% of the people hate you, you're probably doing pretty well, right? So anyway, this brings me to the main topic of my talk tonight, which is stewardship. So what does stewardship mean? A steward is someone who's entrusted with property. They're responsible for maintaining property that's been entrusted to them. And this is the word that I like to use in describing how we approach evolving the Java platform. I think as Java developers, we all feel a kind of sense of ownership in Java. It's like our primary tool, it's the tool we work with every day, and we take it very seriously. So for us, stewardship means ensuring that the Java language and the JVM remain suited to the combination of programming problems and programming environments that we're going to find today and tomorrow, and at the same time, still being recognizable as Java. So when I talk about not making incompatible changes, we of course include in that we don't want to break your code. But compatibility is a lot more than code. So the people part of the story matters as well. We don't want to break our users' expectations or their confidence that Java is just going to work, or their mental models of how things work, or the value of the investment they've made in their skills. each of these forms of people compatibility also places constraints on how we might evolve the platform. So, my job includes, shaping the user-visible programming model, the Java language and the Java libraries. And of course, in the community, there are many people who are happy to help me with this. I get helpful suggestions all the time from developers in the community. Sometimes helpful in quotes, sometimes genuinely helpful. And there's, I notice there's sort of a little bit of a disconnect between what I do and what people think I do, so I made some fun charts to kind of illustrate the difference. So this is one possible view of what an industry-focused language designer does as viewed through, the perspective of maybe an academic. So, in this view, you've got some obvious corporate responsibilities. And then, it's mostly about features, right? More expressive type systems and implementation and all the technical aspects of language design. And of course, those things all are part of my job as well. But the reason I put this slide up is it omits the human side, which is also an important part of my job. So, if we're looking at a particular feature, we have, just like anybody else does, we have a budget. We have a time budget, we have a resource budget, and we also have what we like to think of as our complexity budget. And we don't have big fancy spreadsheets for tracking our complexity budget, but we do realize that the more complexity that we heap on the user, the more we risk distracting them from the important part of their job. Right? When you're writing code, you want to be focused on your business problem. You don't want to be thinking about, how does the language work again? That's distracting you, and that wouldn't be creating value. And that's what happens when you exceed your complexity budget. So if a feature is too complex, it can do a lot of damage. It can do damage both directly by people misusing it, and indirectly by distracting you from your real work. So we're very mindful of the complexity that we heap on users. We're also mindful of how the Java language has evolved, because that has an effect on everybody's perspective and everybody's view. So, even ideas that are simple and otherwise sensible, we might discard them completely on the basis of cultural constraints because they're too different to what Java developers are used to. So, I'll take an example. In Scala, if you have a conflict between two traits that you're inheriting from, there's a very simple rule for determining which one wins. It's whichever trait is listed first in your inheritance clause. So if you say A extends B and C, and there's a conflict between B and C, then B wins. Totally sensible way to do it. When we were called upon to come up with a mechanism for resolving inheritance conflicts and default methods, we thought about, well, maybe we should do it that way. And then we thought further and said, well, Java developers have like 20 years of experience being told that the order in which you list your supertypes doesn't matter. And that would have felt like pulling the rug out from under them and saying, oh, just kidding, everything you know, forget it. So we don't want to do that, right? And so sometimes you can have a perfectly reasonable idea that just doesn't fit the community and it gets rejected on that basis. Now these are considerations I think that someone coming from, say, a Haskell background might never think about. But when you're evolving a platform that's used by millions of people, it makes a big difference. Okay, so this next chart is a little bit less charitable and therefore a lot more fun. This is what I think sometimes that folks in the community imagine that I do based on what they say. So proceeding from clockwise from the top, you have your meetings in secret back rooms, and then every once in a while you poke your head out of the back room and say something obnoxious on a mailing list, and then every once in a while you go to a conference and make some self-promoting comments at a conference, and then from a technical perspective it's mostly about stealing features from C# and of course the most important topic is syntax. Because that's all anyone ever wants to talk about when it comes to evolving the language. And of course it's fun to make fun of people who don't understand what you do, but it's also important to realize that these are the people that we're doing it for, right? And so in some sense what success looks like is not correcting them about how it works, but just making it better anyway, right? What James Gosling said about the feel of Java is supposed to be a blue-collar language. It's a tool for working programmers to get their jobs done. It's not an ivory tower abstraction to be worshipped. There may be a lot of rocket science in designing or implementing it, and certainly in specifying it, but you shouldn't have to be a rocket scientist to use it. And we also care about having a pretty broad range of users because today's cutting-edge users are tomorrow's mainstream users. So We have to consider a lot of different viewpoints. So this last chart feels a little bit closer to reality for me. I mean, and you can see there's some structural similarities with the previous chart. There's a slice for meetings, more politically labeled internal responsibilities. There's a slice for being a jerk on mailing lists, labeled community. But the technical focus is very different. It's not about so much adding features as about keeping features out. And if you look at some languages, you might think that the goal is to see how many features can we cram in this thing. But in reality, adding features is the last thing you want to do, because every feature adds weight, every feature adds complexity, every feature risks interacting with the other 100 features that you've implemented before. And you can't get rid of language features very easily. It's much easier to deprecate a library than to deprecate a linguistic form. So you have to choose your features very carefully, because we're going to be living in them for quite a while. And a perfect example of this, of course, is my favorite, serialization, which has interacted with almost every attempt we've made to evolve the language since then. In fact, in the process of adding Lambda Expressions during Java 8, we literally spent hundreds of hours on the interaction with serialization, and not one of them was fun. Not one. I want all those minutes back. So, the remaining slices over here, which, aren't as exciting, have mostly to do with the consequences of the fact that features interact. And common misperception is that the hard part in a language feature is coming up with the idea, or maybe implementing it in the compiler. And of course, these are important, but we like to jokingly refer to those things as the first 0% of the work, because that's when all the really hard work starts. And the hard work is about fitting them in with existing features and analyzing and testing for interactions, and not only with existing features, but imagining if we did this feature, what future features wouldn't we be able to do because of this? What would it interact with? And analyzing the compatibility consequences of everything. So the really fun part is that little slice at the bottom. It's about yay big, which is what would James do? That's, when you go into your little cave and meditate on what the true spirit of Java is. I get to do that for about a few hours a year. But it's fine. Actually, it's a little more than that. So the biggest slice on the previous chart was compatibility. And we think about compatibility in a lot of different forms. The most important of these is binary compatibility. This is about whether call sites that are embedded in class files continue to link after you change class files that they might depend on. So keep in mind, all method invocations and all field accesses in Java are dynamically linked at runtime by name. So if class A calls a method in class B, the signature from the method gets stuck into A's class file, and then that signature had better be present at runtime. And this dynamic linkage is really one of Java's secret weapons. This is why you're able to just drop a new jar on the class path and everything works. But it's a pretty strong constraint, and we expect that class files that were compiled in 1995 will still work today and will still work, in 20 years. So there's other forms of compatibility. Source compatibility is about whether clients or subclasses will continue to compile after making a change. There's behavioral compatibility. Do things continue to work the same way? Of course, serialization compatibility. Can I change a class and deserialize an old instance? And there's a whole host of more subtle issues, such as changing performance characteristic or memory footprint or things like that. And what makes all this hard is the cross-cutting concern that's sort of fundamental to all of our compatibility analysis, which is separate compilation. Because of dynamic linkage, you always have to deal with the fact that maybe just part of your system was recompiled. I compiled this interface in a library, but I didn't recompile the subclasses. And that's okay. You're allowed to do that because Java is dynamically linked. And normally this isn't a problem if you're following reasonable rules of evolution, like don't delete methods that people might call and stuff like that. But if you're doing things like changing your code generation strategy, or when the generated code for a class depends on information from other classes, which happens when we generate bridge methods, this is when you get into risk of compatibility issues due to separate compilation. And it's happened more than once that we've said, yeah, this is a great feature, we can't do it compatibly, so forget it. Now, that's not to say we never violate any of these kinds of compatibility. I mean, if we couldn't do that, we'd never fix a bug, right, without breaking behavioral compatibility. But sometimes there are bugs we don't fix because of behavioral compatibility. So, it's not a hard and fast rule, but, we'll, in order to consider, breaking compatibility, we have to think long and hard. We have to quantify how much code would be affected by this, and consider what the net effect is on the ecosystem. It's definitely not something we do lightly. So, a lot of people think we're kind of crazy to be so obsessed about compatibility. My claim is there really isn't any other responsible choice, because if you have billions of lines of code out there, and I have no idea how many billions of lines of Java code out there, but it's a lot, pretty much any incompatible change is going to break someone's mission-critical code. And it takes a certain kind of arrogance to say, yeah, you should break his code, because his code is dumb, and it's for his own good. You'll teach him to be a better programmer. We actually get this suggestion a lot, maybe not in exactly those words, but that attitude is not completely uncommon. And I'm sure they think they're being helpful and not arrogant, but the reality is they're only focusing on part of the picture. So, get it? Good, evil, good, evil. Depends on what part of the picture you're looking at. So, what I see is that developers, not surprisingly, tend to overestimate the importance of code and underestimate the importance of stable programs. Now, you can understand this, right? What do developers look at all day? Code, right? So that's the part of the picture they see. But, these optical illusions, depending on what part of the picture you look at, you might come to a different answer. When users look at a language feature, they're usually imagining what kind of code they could write with it that they can't write without it. When we look at a language feature, we look at that, but we also look at the rest of the picture of not only how might it be used, but how might it be misused. How might it interact with other features? How it might change the style in which developers program. How migration of existing code to use the new feature might cause subtle changes elsewhere, and whether those changes are good or bad overall for the ecosystem. So it's not just about your code, it's about everybody's code, and that's a very different perspective. So, just because you're constrained by compatibility doesn't mean it's impossible to evolve a language. It's harder, for sure, it's harder. But it just means that your approach is a little bit constrained. So, we're not allowed to change the meaning of existing programs. So, our next best trick is to assign meaning to programs that didn't have meaning before, right? And this is why it's difficult to evolve languages that have had so many features stuffed into them, because almost every possible symbol of characters in Perl is a valid program and has some meaning. And there's no empty nooks and crannies to shove new functionality into. So ideally what you want to do is add features so that they abstract over existing features. So rather than adding a totally new feature, extend an old feature to a broader range of situations, because this builds on users' existing knowledge and their existing mental models, and it's less likely to create weird new interactions. And the hard part here is coming up with a sensible semantics for the enhanced feature such that when you restrict it to the conditions where it was previously valid, they match the existing semantics. So an example of this trick is what we did with default methods in Java 8. So if we were starting from scratch, building an object-oriented language with multiple inheritance of behavior, we probably wouldn't have done it exactly the way we did it in Java 8. We probably would have ended up with something more trait-like, but we weren't starting from scratch, and we still had to come up with a set of rules for resolving conflicts between declarations in multiple supertypes. So to summarize it briefly, before Java 8, interfaces could only contribute types and not behavior. And in Java 8, we enhanced them to be able to contribute behavior as well. So in the old model, you've got your interface I, you've got your class C, which doesn't implement I, and then you say D extends both C and I, and all of a sudden, the compiler looks at it and says, well, you're inheriting the signature from both of these supertypes. One of them has a method body. You know what? I'm going to call them the same method. I'm going to merge them together. Everything's great. And D has one method called M, which which it inherits the behavior from C and which implements the signature in I. Now in Java 8, we extended this so that you can add a default implementation to a method and interface. And the way you do that is pretty straightforward. You mark the method as default, you give the method a body. And now we have a conflict. D is extending C and I. Both C and I have an implementation, so we need a way to resolve it. Like I said, we thought about, could we use linearization? No, that doesn't work for the way Java developers think about things, so we're not going to do that. Do we want to call this an error? Well, if we call this an error, then adding a default body to a method would not be a source compatible change, because I make a change to I and then I recompile D, and all of a sudden D wouldn't work anymore. So that isn't so good. So, you know, we had to come up with a set of rules for resolving these kind of conflicts, and we came up with a fairly simple set of rules. It started out as a very complicated set of rules, and we worked it down through 7 or 8, you know, iterations until it actually got down to a simple set of rules. And, you know, there's a standard trick here, which is adjust the rules so that, you know, you work through things in steps, and step 1 is the old rules. And you only proceed to step 2 if you end up with a program that didn't have meaning under the old rules. So when resolving a conflict like this between multiple supertypes, we have 3 rules. The first one is really simple. If there's a method in a superclass, ignore the behavior that you would inherit from an interface. So classes win over interfaces. This is the rule that gives us absolute compatibility with anything that worked in Java 7 works exactly the same way in Java 8, because if you find an implementation in a superclass, you're done. You don't even look at the interfaces. And then, you know, if you have a default you're inheriting from 2 interfaces and one's a subtype of the other, the obvious things happen. We prefer a method from a subtype over a supertype. And then rule 3 is there's no rule 3. If you have a conflict and it isn't resolved by rules 1 or 2, the compiler says, you're trying to inherit this method from 2 different places, I have 2 different implementations, you gotta do something for me. Pick one, make your own, but you know, you tell me what to do. And this is exactly what I meant earlier by adjusting a feature to fit in with other features. The rules that we arrived at, that implementations and interfaces are just defaults, and they're sort of second-class implementations compared to you know, method bodies and classes. This isn't what we would have come up with if we were inventing a language from scratch. But that's okay. There's more than one reasonable way to design a language, and these rules are reasonable. They're consistent, they're easy to understand, you know, there's more than one way to do it. We used the same trick when we added autoboxing and var-args in Java 5. We adjust the method overload resolution rules such that first you apply the old rules, and then if they don't work, then you proceed to apply the rules involving boxing and the rules involving var-args. And then again, that was all for compatibility, so that anything that had meaning the day before has the same meaning the next day. So there's a subtle irony to this, the accusation of being kind of obsessed with compatibility, you know, that we don't have the courage to make incompatible changes. And I've been searching for an analogy for how to explain this, and I haven't come up with a good one, so this is what you get. So Central Park, about $500 billion worth of undeveloped real estate. That's not something that happens by accident, and that's not really a stable equilibrium, right? This probably represents the world's largest tract of undeveloped, most valuable tract of undeveloped real estate. Now, I'm sure it's occurred to every real estate developer ever. Wouldn't it be cool to build a building on 60th Street, right? And why would it be so cool? Well, right now, parkfront property is 59th Street, and 59th Street property is very expensive. And why is it expensive? It's not expensive not just because it's on the park. It's expensive because if you buy a building there, you have a reasonable expectation that the park will stay there. That we're not going to build on the park next week or next year, right? And so the value of property on 59th Street is contingent on this collective discipline, which is really unlikely, that we were willing to leave $500 billion worth of real estate completely undeveloped. Now, of course, the problem with letting people just build one building on 60th Street is then, you know, the next guy is going to want to build on 61st Street, and eventually, you know, we've paved over the park. So here comes the strained analogy. Java remains the world's most popular programming platform precisely because we haven't screwed over our customers. We haven't broken your working code. Class files that compiled 20 years ago still run today and will still run in 20 years. And the only reason people think that we should just have the courage to make incompatible changes is they've never seen the carnage that would result from that. So the weird irony is, the more discipline you have, the more you get ridiculed for having that discipline, right? No good deed goes unpunished. Now, every once in a while, I start to doubt myself, and I wonder, like, maybe we really do take this compatibility thing too far. And then I try some other languages, and such thoughts disappear very quickly. So, like, 5 years ago, I built this small system in Ruby to do, like, transcoding and organization of digital media in my house, because I, Had too much time on my hands. And it was a really fun project. It was a great project for learning Ruby, and it actually works. It's still running in my house today. Then I upgraded my Linux server. And turns out in the intervening years since I had last upgraded the server, Ruby 1.8 had been, end-of-lifed, and it installed Ruby 1.9 on my system, and my code didn't run. Because the language had changed between 1.8 and 1.9. Not for any good reason that I could tell, but I spent a few hours, having forgotten all the Ruby I'd learned, trying to fix it, and that didn't go anywhere. So then I spent a lot more hours just resurrecting some ancient creaky Ruby build on my system just to keep my damn, media program running. So, the outcome of this story is that, the investment that I made in building the system was devalued by decisions that were made beyond my control, and needless to say, as a user, I didn't like that, and I don't want to do that to your code. So here's a little story from the evolution of Java that kind of illustrates how the cost-benefit equations can change when you have so many users. So in the most recent version of Java, we finally, yay, added Lambda Expressions, which actually, there's a lot of good illustrations here of the challenges of stewarding a mature platform. And the concept of Lambda Expression is straightforward enough, but, there are a host of challenges, like how do you interpret the notion of Lambda Expression in a way that fits in with what's been done before in the language, and so it doesn't look nailed on the side, and doesn't exceed your complexity budget, or break your code, or make it so that 9 million developers can't do their job till they go back for more training, and do it in a way that people can gradually migrate from their old code to their new code. There's a simple idea, there's still a lot of decisions to be made. And so what starts out as a really simple problem turns out to be riddled with all these soft constraints, that have to be carefully balanced, and they're all about compatibility. Compatibility with code and compatibility with people. So, in a statically typed language, if you add a new kind of expression, you need to be prepared to answer what is the type of that expression. So if you have a Lambda expression, the first question you have to answer is, what's the type of this thing? Now, there's kind of an obvious answer to this question, right? A function type. It's a function from int to int, right? In every language that has lambdas and has types, starting with the type lambda calculus, the type of a lambda expression is a function type. Obvious, right? Well, not only is this answer obvious, I'm going to argue that it was the wrong choice. And I have a whole hour-long talk on why it's the wrong choice, but so I'm just going to give you the 2-minute highlights. So when you design a language feature, you don't get to just design the part where it meets the user, the language syntax. You also have to design where it meets your compilation target. So, and users may claim, oh, I only care about the code. I just want to be able to write this code. It's your job to make it run. And, but if you don't have a clean way to express the code in terms of your underlying computing model, you're going to have performance potholes and complexity and corner cases and puzzlers, and then the users will complain. If you say the type of a lambda is a function type, you need a way to express function type in the JVM. And so many questions ensue, like, what would the type signature look like? What would the bytecode be for function invocation? Do we need a new bytecode for that? How do we create an instance of a function type? Do we need a new bytecode for that? And how do we map variants at the Java level into the VM type system, right? We have you have a function from question extends, question super t to question extends u. Well, we have variants at the language level. JVM type system doesn't have variants. What are we going to do about that? Lots of questions to answer. So the JVM doesn't have a native way to represent functions, but we could invent one, of course. We could add new type signatures and new bytecodes and new verification rules, and that's all really fun. That would be expensive, but we could do it. Or we could do what BGGA proposed, which was simulate function types with generics. But that would suck because generics are erased. So we would end up with function types that are boxed and erased, and that's not so cool. The bottom line here is that if there's a gap between the language and the underlying representation in bytecode or native code or whatever you're compiling to, it always causes problems. And so you have to design things so that they work cleanly throughout the stack, even though it's not the part the user sees. So instead of doing this, we kind of backed off from the, what's the perfect way to do this, and we doubled down on the, what are Java developers already doing? And it turns out there was a really good answer here. We looked at how Java developers abstract over behavior without function types, which we've been doing since day one, and there's a pretty straightforward answer. You write an interface with one method. Runnable, callable, comparator, action listener, right? We've all been doing this for years. We didn't know, we weren't thinking of them as nominal function types, but that's kind of what they are. this code that we could have written in 1997, we're using action listener as a nominal function type. It's something that consumes an action event and returns nothing. Now, ignoring the syntactic pain of inner classes, this works out pretty well. You know, everything's cleanly typed, and you can represent primitives and references without boxing and without erasure, and all that's pretty good. So we decided in the end, let's just take this mechanism, this idiom, and we'll formalize it by giving it a name. Names are powerful things, right? We're taking these interfaces and we're calling them functional interfaces. You had no idea you've been programming with functional interfaces for years, right? But you have been. And of course we define a conversion from a Lambda expression to a functional interface so that we can take this Lambda expression that takes an action event and performs that action and convert it to an action listener, and in fact we can add some type inference so that we can infer some of the type information from the signature, and we're done, right? So what we did here was we saved a huge pile of our complexity budget. And instead of introducing function types into the type system, which would have had a big cost, instead we just gave a name to an idiom we were already using. And this is the kind of thing that would be totally non-obvious if you're coming at it strictly from a type theory background, right? But if you're coming at it by looking at what kind of code do Java developers actually write, it sort of should be obvious. Now, there were lots of other obvious but wrong ideas that presented themselves during this exercise, and I can't list them all now, and I don't even have any concrete advice for how to identify when an idea is obvious but wrong, except to be aware that it happens a lot. And so if you come up with an idea that you're really excited about, sit back and think about it for a few months, and there's a good chance when you come back to it, it's not as perfect as it seemed at first. So a certain degree of skepticism is warranted, and the best thing that we can do as language designers is to move slowly and deliberately enough that we have the opportunity to catch these things before they're released as mistakes into the wild. So it turns out that this decision to embrace nominal function types instead of structural ones paid this enormous dividend that we didn't even see at first. So imagine it was really easy to add function types to Java. So we would have forged forward, added structural function types to Java, patted ourselves on the back for having done such a fantastic job. Now what's going to happen? We've released Java 8. Now, one of the assets of the Java ecosystem is there's lots and lots of great libraries. So if we introduce a better way to represent behavior in the type system, what are people going to do? They're going to rewrite all those libraries. And it's going to take years. And we're going to go through this long migration period where we're, first of all, wasting a lot of effort migrating libraries and dealing with, oh, this library depends on that library, but it hasn't migrated yet. It's 5 years of churn for no value. What a total waste of time. These libraries are fine. And in fact, by picking an idiom that existing libraries already use to model behavior, we achieve this really rare kind of compatibility, which is forward compatibility, where libraries written in 1997 that had no idea we were ever going to add lambdas to Java are usable with lambdas from day one without being recompiled. That's pretty cool. So, because doing real function types turned out to be hard, we kind of dodged a bullet by not wasting a lot of people's time in a big, expensive transition. So, less is more.
When you're saying that the code was written a long time ago and working in this world of lambdas, does that mean that sometimes, in some way, that code really is making use of lambdas?
Sure. So take this example up here. You have a library that defines a type called action listener that people were using with inner classes, and without recompiling that library, I can pass a lambda to it, and the library just receives an instance of the interface action listener.
Yep.
And it has no idea that this action listener started out life as a lambda. All it knows is it's an object that implements action listener, and without even having recompiled that library. It's a pretty cool thing. So, where was I? Yes, all right, so the choice not to do function types kind of points out another lesson here that's pretty worthwhile, which is, if you don't know the right answer, maybe just don't do anything. Certainly don't do the wrong thing. If we had gone ahead and pressed forward and done some kind of deficient function types like what was proposed in BGGA, we might be in a real mess. But if you have the discipline to leave it alone, you get a chance to come back and do it later, and do it better. And a good example of this is at Java 1 last year, James Gosling told a story that someone asked about why weren't generics part of the first version of Java. And it's certainly not because we didn't understand parametric polymorphism in 1995. I mean, all the important papers about parametric polymorphism had already been written by then. And it's not because we thought it was a good idea to have a type system so weak that you put strings into a collection and they come out as objects. It was because we didn't know how to do it right. And if we felt like Java 1.0 must have generics, what would we have gotten? We probably would have gotten C++ templates, right? Or maybe we've gotten patterns from Beta, if you remember those. So it might have taken a long time, in fact, quite a long time to get generics, but the generics we got were a lot closer to the spirit of the language, and I think the generics we would have gotten in 95 would not have been. So if you don't know the right thing to do, at least don't do the wrong thing. And if that means doing nothing, then that kind of has to be okay. All right, so I talked about how not doing structural function types saved us a lot of complexity budget. So here's an example of where we spent it in a more effective way. So here's a quick example, some code you can write in Java 8. Filter MapReduce on a collection. Got a collection of people, and I want to say, take the people, pick out the ones that are male, for each one of them get their weight, and pick the largest. So this is find the weight of the heaviest guy in this collection. Now, this is a style of programming that you've been able to do for years in Ruby or Python or JavaScript, or name your favorite other language. So it's really easy to say, oh, big deal, Java finally caught up. And you'd be right. We finally caught up. It took a while. But let's take a look at what the big deal really is. The big deal is how we integrated it into our libraries and the result that we got. So first of all, we integrated parallelism into the model. So if you want to do this, this operation in parallel, and your data source is a suitable data structure for parallelism, and certainly these operations scale really well, all you have to do is say, I want to do this stream in parallel. And you'll get a parallel decomposition. Well, that's pretty cool. And Java has had support for parallelism for years, but it's always been the sequential expression of code and the parallel expression of the same code looked radically different, which meant that if you wanted to go parallel, you had to rewrite all your code, and that wasn't easy. So, but the real benefit here is the power that's kind of beneath the surface. And it belongs beneath the surface. So like all the collection implementations got retrofitted to support decomposability, so all the collections can be used as sources for parallel streams. And it may look like this, this pipeline is doing 3 separate operations, filtering, mapping, and reducing. But in fact, they all get fused together into a single pass on the data, whether it's a single sequential pass or a single parallel pass. And kind of as a bonus, the implementation tracks characteristics that it knows about the source. So for example, if the source of my collection was a sorted set, and then I filtered it, and then I asked it to sort it, the implementation would say, I know they're already sorted. The source was sorted, filtering is order preserving, so sorting is a no-op, so I just won't do that. Right? And this is all based on sort of under the water characteristics that get passed down from the source through the pipeline. And that stuff is all hidden, and that's where it should be. It should be hidden because, as a developer, you want to write, what does this code do? And you'd like for the system to figure out the right way to optimize it. So not only did we catch up to some other languages in expressiveness, we really leapfrogged them in terms of performance. And not having blown our complexity budget on foundational issues like function types let us spend a lot more time here where it has a really big impact, for the users. Now, you might look at this code and say, okay, but big deal, if I'm going to write this loop as a loop, it's not really that ugly, is it? Right? In fact, it might even be a little shorter. But more complicated Java code tends to get ugly fast because there's a lot of accidental detail that leaks out. So here's an example of some typical idiomatic Java code that does a query on a collection. And it doesn't matter what it actually does, but the key point is if I said, okay, someone tell me what this code does, you're all still reading, aren't you? Right? And if you have to read it that carefully, there's a good chance you're going to make a mistake. So if I recast this code as streams code, it's a lot more obvious what it does. Take the transactions, filter them to select the ones whose buyer is over 65, for each one get the seller, throw away duplicates, sort them by the seller's name, and print them out. right? It didn't take 20 or 30 seconds to wade through that code to figure out what it does, because the code reads like the problem statement, and code that reads like the problem statement is more likely to be right. So, you've probably seen these examples before, but my point here is it is possible to teach an old dog some pretty cool new tricks. Okay, so let's take a look in the future. We've got Duke in his lab coat. Java 8 was a pretty cool upgrade, probably the biggest upgrade that we ever did to the programming model. So people are excited about Java again, that's pretty cool. So what's next? Well, so our approach for picking evolutionary targets is a pragmatic one. We try to pick the biggest pain points, hammer away on those, and move on to something else. So in Java 8, they were mostly about expressiveness, abstracting over behavior, lambda streams, etc. For Java 9, the big pain point that we're aiming at is programming in the large, module systems, reliable configuration, etc. But pain points can originate in the hardware as well, and since we want Java and the JVM to continue to perform well on the moving target that is modern hardware, ultimately we will have to occasionally refresh the JVM's relationship with the underlying hardware. So, speaking of hardware, how has hardware changed in the last 25 years? Short answer, lots, right? So, in the old days, you had, single core, single socket systems with no pipelining, no instruction level parallelism, no caches, and relatively small memories. And the performance model in those days was really simple. You could count instructions, right? And it took about as much time to do a memory fetch as it took to do an arithmetic operation. And over time, our systems got more complicated. We added cache, we added more layers of cache, we went multi-socket, we went multi-core, memories got bigger. And the cost of all of this is that the cost model became less predictable. So if you're doing a memory fetch, maybe the data you want is an L1 cache, and that's only going to take a couple cycles to get your data, but maybe the data you want isn't in any of the caches, and you're going to go all the way out to main memory, and that's going to take a couple hundred cycles. And at the same time, our cores got fancier, so that with deep pipelines and superscalar execution, and like a modern Intel chip will issue 4 arithmetic operations on a clock cycle. So if a cache miss is costing me 300 clock cycles, and I can issue 4 instructions per clock cycle, this could be costing me 1,000 instruction issue slots to take a cache miss. That's a pretty big difference from the cost model I described, from like 1985. Now it stands to reason that given these changes in the cost model, whatever trade-offs we made in 1995 about how to lay things out in memory are probably not optimal for today. It is possible we could have gotten really lucky. We didn't get that lucky. Over time, this turns into challenges for cost predictability, and it turns into costs showing up in places that we didn't expect them. So if you think about the JVM type system, it's pretty simple. You got your 8 primitive types, you got arrays, you got classes. And you can model anything in the world with this, right? It's perfectly flexible. The problem is, it might be more flexible than we want. All objects have identity. Identity exists to serve mutability and polymorphism. Sometimes we don't care about mutability. Sometimes we don't care about polymorphism. Sometimes we just want a carrier for a complex number, real and imaginary, or something like that. And we don't need objects for that. So the problem is that JVMs have done a really good job at slicing through code complexity. They haven't done as good a job at slicing through data complexity. And so we can't necessarily predict when an object is never going to use its identity, because someone could, anytime, anywhere, use any object as lock. Synchronize O, lock. So the VM has to be pessimistic in how it lays the data out. So to illustrate this, imagine we've got a simple class represents an XY point. And we have an array of these guys, which you can hardly see. And an array is an object with an object header, and each element of the array is a reference to a point. And each of those points is an object with an object header. And each of those has to be allocated on the heap and garbage collected when you're done. So let's sort of add this up on a memory efficiency perspective. For 2 words of data, my x and y, I'm using 2 words of header overhead and a word of pointer overhead. So that's like 150% overhead. Now, how many people here would like to be able to put a larger data set in their heap? Well, one way we can do that is by not being so wasteful in the way we lay things out. Worse than the memory overhead is the cache inefficiency of this. every time you traverse one of these pointers, you risk taking a cache miss, right? Remember that 1,000 to 1 penalty? I mean, that's the theoretical penalty, but it's, you know, it's measurable. And the reality is, you didn't necessarily want this layout. This is just the layout you got. The layout you wanted was probably something like this, right? And the memory access characteristics of this layout are really nice, because when I pull that first X into cache, I'm going to pull the next 7 or 15 words into the cache line, and by the time I've looked at the second one and the third one, the hardware prefetcher has kicked in, and it's already pulled the next one into cache. So traversing this is an awful lot faster than traversing that. And you didn't ask for this. You kind of wanted this. It's just what you know, you got the other one, right? Now, sometimes, you know, your data set is small, you don't care, your program doesn't have strict performance requirements. But you know, if you're doing high frequency trading, you care about every cycle, right? And you'd like to be able to squeeze these costs out of your program. Now, when confronted with this situation, developers often will take matters into their own hands, and you know, sometimes they have to, sometimes they just can't help themselves. But they'll do tricks like this, right? They'll shred this array of x, y points into 2 arrays, one of x's and one of y's, in the hopes of regaining the locality. How many people here have seen code like this? How many people here have written code like this? Right? I think more hands should be going up on the second one, but you're embarrassed, and for good reason. It's an ugly trick, and you know, we shouldn't have to do it. The sad part is, like, there's a lot of developers out there that do stupid stuff like this for performance reasons, with no actual evidence that their code isn't already fast enough, or in fact with no performance measurements at all. But regardless of whether we do this out of genuine need or out of a destructive obsessive compulsive disorder, we should stop putting developers in a position where they perceive that they have to choose between good abstraction and encapsulation and performance. So that brings us to a feature for today's hardware, value types. So if we recast this point as a value type, what we're saying is we don't care about the identity and all the things that bring with it. We don't care about mutability, we don't care about polymorphism, we just want to treat it as a value. And so values are implicitly immutable, implicitly final, and you compare them by value. 2 points are the same if they have the same x and the same y, not if they have the same pointer. And that means we can pass them on the stack or in registers instead of on the heap, and it means that we can flatten their state into arrays with no loss of semantic usefulness. And values can have other things that classes have. They can have methods and constructors and fields. They can even have private fields and private methods. They can be generic. And because they're not polymorphic, there's no dispatch cost to calling their methods. They're just like static methods. So the mantra here is codes like a class, works like an int. If you have a value that's a field of another class, the fields of the value will just get inlined right into the enclosing class. Now, the applications for this are pretty obvious. Numerics like complex or decimal, tuples, algebraic data types like optional or either, STL style cursors, the list goes on and on. Now notice that this has nothing to do with expressiveness. This doesn't allow you to express anything that you can't already express with objects. It just lets you do it in a way that's more memory efficient and cache efficient. So by making the right thing also be the fast thing, we remove this whole source of friction from the development process. How many people here have had the experience of, like, you have to declare some little class as a holder for things, and there's this voice in your back of your head saying, oh, I don't want to allocate an object for that, right? And in the end, you allocated the object and it was fine, right? But the, oh, I don't want to do that, is a source of friction. If we can eliminate that friction and have you know, I'm expressing the right thing and it's fast, woohoo, we win, right? We get to go home early. So, you know, and because value types have access to encapsulation, you know, just like classes, we can use them as like secure, cost-free wrappers around sensitive state, like, you know, internal references or native pointers. And so you kind of get a layer of type safety without a layer of cost. So safety, maintainability, and performance. Free lunch, woohoo. So, okay, what about generics? How does this interact with generics? You know, if you want to create an array list of ints, well, you can't do that. You have to create an array list of integers, right? How many people find that annoying? Yeah, you all do, don't you? I find it annoying too. So we see exactly the same layout that we saw in the previous example, right? You've got your array list, it points to an array, the array points to a bunch of integer objects. This one's even worse. You have a 4-for-1 space penalty because you only have one word of data in your integer. Now, really what people want all along is just to have an array list of int and have it be backed by an int array, right? Who wants this? Yay. Okay. So, from a language perspective, once we add value types, you immediately kind of see that this breaks the uneasy compromise we made in 2004 that you can generify over reference types but not primitive types. Because there were only 8 primitive types, and so like all the infinite number of types except 8 is still almost everything. But like all the reference types but none of the value types, that's like half. That would be terrible. So, you know, we realized that this uneasy compromise falls apart, and, you know, so generics really have to work with values, and, you know, so we're going to have to bite the bullet and support specialized generics, which is a big deal, but it's worth doing. And so these two features together, value types and being able to do generics over values and primitives, they're part of actually a bigger effort to reboot the JVM's relationship with memory and memory layout, and to balance the need for abstraction and encapsulation with the performance realities of modern hardware. But it's another pretty cool example of teaching an old dog some pretty cool new tricks. So, okay, time to wrap up. I'll close with a little bit of warning. Be careful what you wish for, right? At the beginning I said, you know, we all want the software we write to be successful and used for many years, right? But success brings with it costs and constraints that can be pretty frustrating at times. On the other hand, you know, these constraints, most notably keeping the promises to your users, whether you made those promises explicitly or implicitly, they really force you to spend a lot of time up front thinking about the consequences of your decisions and what the, you know, what the possible interactions might be. And most of the time, thinking deeply about what you're doing pays off, even though it means you might not be able to rush forward as quickly as you might otherwise want to. So, with that, I'll finish up, and I'm happy to take questions. All right, we'll start here, and then we'll go around that way.
When you say that value types would be immutable, do you mean immutable in the way that like I can change an int, but I can't change the value of 3?
Correct. And you can't take an int and change the 7th bit of it, right? You can store an int in a mutable field, but you can't change 3, and you can't you can't access the individual bits. You can only access it as a whole.
But if I were to change a point to be a different one, would I be allocating a new object and dumping something regardless?
There's no objects. So if I have a value that is an xy point, so it's essentially 2 fields glued together. And if I want to update it, I overwrite both of those fields with 2 new fields. Now, if you're overwriting it so that one field is the same as the old value, the VM's going to figure that out and eliminate that as a dead store. So it's not as inefficient as it sounds. But you're not. It's not a pointer to an object on the heap. It's, you know, just like a long takes up, you know, 2 32-bit slots. You know, a value might take up 1, 2, 3, 5, you know, 7 slots.
Okay. Thank you.
Sure. You right there, sir.
Okay. So you said that value types were made primarily as a performance concern, but kind of in the ecosystem, do you see them having an impact on how people develop? Because now there's this language level constraint that, or construct that gives you mutability, kind of immutability for free, whereas, you know, a lot of people, you'll have to write just like a class where you only expose getters, and then also because it basically completely disallows inheritance. So at kind of a code-based level, if your organization doesn't like that, you just say, sorry, only use value types. So what kind of impact do you see that having on the ecosystem?
So that's a good question. The answer is complicated. So first of all, we're not deprecating objects. So you always have the choice, right? And now with choice comes responsibility of which of these is the right tool for the job. The sweet spot for values is relatively small aggregates. You know, a complex number, an xy point, a tuple of 3 things, you know, a quaternion of 4 values that I'm using to transform a graphics display, things like that. A value type with 50 fields is probably a mistake. It's not necessarily a syntax error, but it's probably a mistake because you don't want to be passing something like that by value. And, you know, if you read the C book, they tell you if you pass a struct instead of a pointer to a struct, you're going to pass the whole thing by value, and if it's big, that's dumb, don't do it. Right? So it's the same kind of thing. There's some things that values are great for, and some things that they're not. And I think, as always, it's going to take us a little bit of time to learn what those new idioms ought to be. But I think of it as supplementing the tools we have with new tools that are good in specific situations. And then it becomes an education problem to communicate to people what the right way to use these tools are and the wrong ways.
Is there a tool in another programming language that you think is a close analog to value types?
So obviously C has structs. C# has something called structs that aren't exactly like structs in C. They're sort of halfway between C structs and value types. So there's plenty of precedent for I want to describe an aggregate that I'm going to inline into other aggregates and flatten into arrays. Is there a language that does it exactly the way we're anticipating? I don't think so. But the concepts are pretty straightforward and pretty well understood from other languages. All right, how about that gentleman back in the corner there?
Hi, thanks for a great talk. I was wondering, do you need a value keyword to do this, or can you just take final classes that have final members like you had previously and just say, okay, we're going to make those value types or something?
So a final class with final members can still be used as a lock, and it still can be compared by reference, not by state, and it's still passed by passing a reference as opposed to passing its state by value. And it doesn't, classes like that have existing semantics that we would have had to have undermined. And it's a little too subtle, right? To have, to add the final keyword and have the performance model change so completely, I think would be subtle. We're intending that this is a feature for advanced developers, for people who are building performance critical systems. Doug's going to be all over this, right, for building data structures. It's great for that, but it's not necessarily something that every Java developer will come into contact with. They'll certainly like the generics over primitives, though. All right, who else? Let's start in the back and come forward. Try to minimize the distance that Frank has to run.
First of all, thanks for the whole compatibility has been there for such a long time. Questions regarding the parallel streams. So in case of parallel streams, is there any plans to have a parallel stream that would take an executor as an argument?
Yeah, so the question is, when you execute a parallel stream, it just executes by default in the in what's called the common thread pool. So the JVM will spin up a thread pool for use by sort of everybody who wants to for doing parallel decomposition. And the question is, will I be able to pass my own thread pool in? We thought about this for a very long time, and you're going to hate the answer. The answer is, for every person who uses it correctly, there's 1,000 people that will shoot somebody else in the foot. What we found is if you give people the ability to create their own thread pool, they will. They'll create thousands of them. And then every parallel query will create its own thread pool, and you will have hundreds or thousands of threads competing for your 16 cores, and your performance will suck, and then you'll blame us. So we looked for ways to do it in such a way that it was possible by the few people who really need to, and harder to do by the thousands of people who think they do but don't. But we still haven't found a good way to do that. Yeah, I told you you'd hate the answer.
So how does it? Thanks for the talk. First of all, the value types are the good things. So, is there any plan for now overloading the operators, like primitive operators like plus and minus and things like that, mainly just for the value types?
Wow, it took you guys all a minute and a half to come up with that. You've got to work on that. No, so absolutely, that's the next question people ask of, I can use value types to model numerics, great. Complex, big decimal, what about my operators? So the answer is, we're not sure, we're thinking about it. It's certainly attractive, it's certainly a sensible thing to want to do. We're mindful of the precedents. So our first big experiment with operator overloading was C++, and we saw how well that worked out. And now maybe, like, we could excuse that as, well, that was like 25 years ago, we didn't know anything then, that was back in the days before we realized that putting 17 fonts on one page was not a good idea, but we learned that, and so maybe we've learned some taste about operator overloading too. Well, so our next big experiment on that was Scala. How did that go? Operator overloading in Scala is every bit the unmitigated disaster it was in C++, except that we have 20 years fewer of having an excuse. So that's one of the forces that pushes us away from considering our operator overloading. On the other hand, for doing numerics, it's obviously something that you would want to do. And so the question is, have there been any successful examples of languages that have restricted operator overloading to numeric types only? And there actually have been a few. They're not languages that anybody really uses, but there's at least something to look at and say, all right, this seems possible. So the answer is maybe. We're looking for a way to do it in such a way that isn't the attractive nuisance that it is in C++ and Scala, where people get brilliant ideas like, let's overload the shift operators for I/O. But if we could restrict it to numerics, sure, that'd be great. But in the meantime, we got a lot of other much harder problems to solve, so we're working on those first, and then we'll come around and have a swing at overloading.
Expectation-wise, maybe I would go a little further, where maybe the operator overloading execution should be allowed in parallel stream fashion.
That's taking it a little far. But we have some ideas. We have some ideas. We're thinking about it.
Thank you.
Sure.
I have a question about a different topic not covered here. This is the flow class, the reactive stream model API in the .NET. So basically, I found that, this is only my personal experience, I found that interface classes a little bit hard to use, in the sense that basically you're not a functional interface. So in order to subscribe from a producer, you need to implement full methods. Is it going to stay like that, or is there going to be any way of having that laid out as a functional interface that we can use Lambda?
So the flow classes were not designed by us. They're essentially pulling in the design that's been done by the reactivestream.org folks. So the value of having that in the JDK at all is compatibility with other APIs that implement that. And so we don't want to go ahead and refactor that or redesign it, because that wasn't our goal. Our goal was to include something in the JDK that would tie together all those different implementations. So we were pretty heavily constrained in that choice, because it's not our API, it's somebody else's API.
Yeah, I kind of agree with that, but as far as I know, there's almost like 0 implementations of that right now.
Yeah.
There's compatibility classes to adapt from all the implementations, but not pure implementation of that.
It's like we had one over here, and then we had somebody in the front.
So in the example you gave of lambdas, you were basically adding syntactic sugar to the compiler to do something you already could do.
Go ahead, finish your question, and then I'll...
So my question was, why couldn't I then pass a target 1.2 to the compiler and have it run on a Java 1.2?
Oh, okay, so there's two questions there. I'll start with the myth that lambdas are just syntactic sugar for inner classes. They're not. They compile to completely different bytecode. They have different semantics. They're doing a similar thing, but they're not just a more syntactically compact description of an inner class. And that's actually important, because the meaning of names inside a Lambda body have a different set of rules, a much simpler set of rules, than the meaning of names inside an inner class body. So anyway, coming back to your question, why didn't we allow -target 8, -source 8 -target 7, essentially, right? And our policy is we don't do that. And the reason we don't do that is it almost never does what you think it's going to do, because language features almost always have companions in the libraries. So when we added the for each loop in Java 5, we added the class iterable in Java lang. So we could have compiled it down to bytecode that would have worked on Java 1.4, except that the iterable class wouldn't have been in the class library. And the same thing is true with lambdas, that there are classes in the runtime library for supporting the creation of lambda expressions, the serialization of lambda expressions that aren't present on a Java 7 VM, in a Java 7 JDK. So we would have had to backport all of the library additions that we added to 8 into 7, at which point we would have turned 7 into 8. And the value of, I want to run it on this old JVM because I'm comfortable with what it is, goes away. Right? So go ahead.
Mostly for running libraries that other people are using an old version of Java.
So the bigger issue is whenever you add a language feature, you put library writers in a situation where they want to ship one jar that runs on 7 and 8. And I think this is the issue you're kind of getting at, right? So in 9, we have actually a kind of cool story for this, which is called multi-release jar files. And the idea is, let's say there's a way to do something in, let's say, Java 8, and there's a better way to do it in Java 9. Or maybe we've taken away the way in 8, we've given you a different way to do it in 9. So what multi-release jar files let you do is say, I've got a jar file, it's got 4,000 files in it, it's got 3 classes over here in the corner that have 2 different implementations. Here's the 8 implementation, here's the 9 implementation, whichever version of the JVM you're running on, pick the right one for, for your runtime. And that allows library writers to, to ship one jar that runs on 8 and runs on 9 even when there are incompatible changes from 8 to 9, or there's an old way to do it in 8 that's kind of lousy and a much better new way to do it in 9, take advantage of that without having to use reflection. So our approach for helping library writers migrate across multiple releases is to make it easier for them to build multi-release distribution units. But trying to target an old JVM or an old JDK with new language features, it's pretty rare that you actually can pull that off. And frankly, we would rather people just adopt the new one because it's fairly expensive to keep maintaining all those old versions. Okay, so how about in the back corner there?
Yeah, thanks for the speech. My question is about erasure. Do you see erasure as I won't say mistake, but do you see it as something as a hindrance now that's used after 2 years working with it? And my second question is that something you'll try to face in the future?
Okay, so the question is type erasure a mistake that is like a stone hanging around our neck? Or is it something that we actually still look at and think, well, that was a pretty sensible compromise, right? Is that pretty much your question? So you'll be surprised to find out that I actually think erasure is a damn practical compromise. People look at erasure and their first reaction is a very unpragmatic one, right? It's, ew, that's disgusting, right? It's an aesthetic reaction rather than a pragmatic reaction. There are a lot of very sensible things about implementing generics via type erasure, including the fact that I'll bet like most of the generic code that we write, including the code that I write, and I'm pretty good with generics, can't actually be expressed in our generic type system without occasionally casting something to foo of question mark or even to raw foo, right? How many people here have had to cast something through raw to satisfy the compiler? Right? A lot of you. And even if like for 80% of you, there was actually a way to do it, you just didn't figure it out because generics are really complicated, there'd still be a lot of hands up, right? There are, so if, in a truly reified generic type system, you would not be able to write that code because the VM would reject it at runtime, right? So it's a practical compromise that allows you to cheat when you have to. And of course, if you cheat at the wrong times, you get what you deserve. But for the most part, it's fairly practical. It's also a fairly performant compromise because it means we only have one version of the list class. We don't have a separate array list of string and array list of integer and array list of array list, etc. So I still like erasure. What I don't like about erasure is sometimes it gets in the way of writing frameworks like serialization, deserialization frameworks, where you're going to turn an object graph into XML or JSON or something like that. And you want it to come out the same way that it went in. That's, I think, the biggest problem people have with erasures, that writing those libraries is hard. I think there are better solutions to fixing that problem, like better type literals. So, you know, our approach is, if we're doing generics over primitives and values, we essentially are reifying generics over those things, because we're spinning a specialized class for array list of int. And because int, you know, the type variable there isn't polymorphic, int doesn't extend anything, nothing extends int, then you really do have a reified implementation. But for the reference generics, we're likely to just leave it the way it is, largely for compatibility reasons, in addition to the fact that kind of ain't broke, don't fix it. So I think it was a practical compromise, although I certainly understand the aesthetic argument of wouldn't it be nice to actually have this type of information at runtime. One last question.
Can you give us an idea about the collaboration model on the Java team? Do you do code reviews? How do you handle code quality?
Okay, so you mean how do we collaborate with each other as opposed to how do we collaborate with the community?
Yes.
Oh, okay. So we have a somewhat heavyweight process. We do all of our analysis and code review prior to commit. So the process of putting back a change is you have a bug that describes what you're going to do, and there's a one-to-one correspondence between one bug, one commit. And before you can put anything back, you have to go through multiple levels of review. So we have code review, and depending on the area that it's in, or the size or complexity of the patch, maybe you need, 1, 2, 3 reviewers. So if you're, putting back a change in some highly security-sensitive code that's known to be, easily broken, like serialization, you might want 11 reviewers for that, right? Like on the garbage collector team, they have a policy that all put packs, get 2 reviews. On the libraries team, we have a more, leave it to your judgment. If you think 1 reviewer is fine, then 1 reviewer is fine, unless there's a security issue. For issues in specific areas that have security impact, we also have to get a review from the vulnerabilities team. So we have a team of security experts that that do reviews for those for those items. And then if there is an API change, like this is a new API that's part of the JDK APIs, we have a separate API review process, which is not about the implementation, but about the quality of the specification. Is the API consistent with other similar APIs, etc. So, something as simple as, fixing a simple bug could be really easy. You pull together a patch, you file an issue in the bug system, you get one guy to review it, they say okay, you wait 24 hours to see if anybody else has any comments, because we do our reviews on public lists, and you push. But for a big thing, there could be multiple rounds of review, there could be multiple people reviewing, it could take weeks. And so it's really, it really depends on the scope of the issue.
Okay, all right. Thank you very much, Brian, for fantastic talk.